So, welcome back student to the next class of complex analysis. So, today we will going to start something called series and sequence. Sequence and series, sequence and series of complex number. So, first let us start with this sequence. What is the meaning of sequence in complex number? So, it is sequence is something, say I represent something like z to the power n is my sequence defined like this. What is the meaning? It is a mapping. Where the map is something like that, I will have some integer, real integer, positive real integer, say n, and it will give me some set of complex number c. So, it is mapping where I will have some integer, I put some integer, and as a result I am getting set of a complex number. That means my domain here is integer n 1, 2, 3, and my range here set of complex number. Okay. So, I have something called sequence. This is Zn, means this is some complex number having some index n. That means it is a function of index n, where n is some integer. So, I will change this number 1, 2, 3, 4, which is related to this n, and then as a result what happened, that every time when I change this number I will generate new numbers, new complex numbers. It may be repetitive, it may be non-repetitive, and these new numbers are the range which is in the set of complex number. This is a subset, rather this is a subset of complex number. This is not set, this is some subset of the subset of some set of complex number. Whatever I am getting is some subset, some amount of complex number I am getting. With this very brief definition, things will be, let me erase this. So, let me give you one example that maybe make life easier. 1 plus I to the power n. This is obviously a complex number, and I to the power n means this complex number, it depends on the value of n, where n 1, 2, 3, 4, 5, and I will have different complex number, and if I put this different complex number, then they will form a sequence, that is all. So, when n is equal to 1, I will have my first number this. When n is equal to 2, I have second number. When n is equal to 3, I have number I minus 1 minus I. N is equal to 4, I have 2. N is equal to 5, I have, and so on. So, that means I am changing my n 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and as a result what I am getting is these numbers, which I call the sequence. Now, the obvious question that should come to our mind is how many numbers I am getting here if I go n tends to infinity, and is this number is going on or it will be converging to some points. So, Next thing is convergence of sequence. Convergence of sequence. Convergence, as I mentioned, if I go, so in mathematical form, if n tends to infinity, if I put n tends to infinity, let me change the chalk here. If I put n tends to infinity, the nth number, nth sequence number, I want to find out the limit for n tends to infinity. Say it goes to some value L. It goes to some value L. This is the mathematical. So that means when I change the value, the number of value when I am changing, so it will try to go to some, try to locate some particular point which I call L. In another way, if n tends to, n is always, if I put n some, I change the n such a way I always, it is always greater than some value n, big N, then I will have this relation, this relation. So let me visualize these things. So this is the domain I have, this is the complex number that is changing. So in the complex plane, the numbers are changing, and it is changing in such a way, this is the domain, here the value is L, and this is epsilon, and the values I am changing the values through this n. So when I am changing, say some point is here, 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 here. So as I increase, the point is, as I increase the value of n, the sequence of the point is tend to go to some specific value L. If that is the case, that means the sequence is converging and converging to the value L. So let me give you another example. Let me give you another example. Example gives life, makes life simpler. So this is another, this is a sequence. The sequence is represented by this second bracket. Inside that I have some complex quantity which is related to the value n. Now I change n, so every time when I change n, I will start getting new values. So when n is equal to 1, I have minus 1. When n equal to 2, I have n equal to 2, then it is 3. N equal to 1 is, n equal to 2, it is 3. So minus I by 2. N equal to 3, when n equal to 3, I have this 3 plus 1, 4, I to the power 4 is 1 and it is 3. So 1 by 3. N equal to 4, when n equal to 4, I have I by 4. N equal to 5, I have minus 1 by 5, and so on. This is the pattern, the way this term is changing. Now if I want to put that, let Let me put the coordinate. Now I want to put this number here in this z plane, and if I do that, then I find n equal to 1 is minus 1. So, first point is, say this is minus 1 here, second point minus I by 2. So, somewhere here this is minus 1 by 2 with I, third point is 1 by 3, somewhere here this is 1 by 3, fourth point is I by 4, somewhere here I by 4, fifth point is minus I by 5. So, somewhere here I by minus I by 5 and so on. So, if I now draw these things, then I can find this function is changing like this and seems to, it is changing like this and seems to go to some value like 0. And obviously, if you take the limit of these things, limit n tends to infinity I n plus 1 n, the result is 0. So, that means this sequence is converging and converging to a value 0. Okay. We will obviously show more examples, so that understanding will be clear, but before that let me, so when limit n tends to infinity Zn is L, that eventually means, I mean, when this is the case, you should realize one fact, that L is a complex number, because this is a complex number and I put this complex number with the limit n tends to infinity. So, whatever the result I am getting should be a complex number. So, L is a complex number, so I can write this as a plus ib, and this limit goes to this point, thus eventually means limit n tends to infinity, real part of whatever Zn I have should go to the point A, limit n tends to infinity, imaginary part of Zn can also go to some point B. So, that means this complex number containing two quantity, one is A and B, both are real, and when n tends to infinity goes to Zn goes to some value L, which is a plus ib, a complex number, the real part of this goes to the real part of these things, and the imaginary part of this Zn goes to the imaginary part of these things. That is essential, so that we can have the limit in our hand. Okay. Now, we go to few more examples and then things may be clear. So, next is this example. Ni plus 2 whole square divided by I n square. Ni plus 2 whole square, let me check it is correct or not, and then n square I. Okay. So, I need to find out, we need to find out whether this sequence is converging or not, this is a converging sequence or not. So, that means I need to find out this quantity, limit n tends to infinity, whatever the quantity I have here, Ni plus 2 whole square divided by I n square, this limit, just all. So, if I evaluate this limit, and if this limit gives me some value other than infinity, then I can say that this is converging. By the way, I need to mention one thing also. So, limit n tends to infinity Zn, if it goes to infinity, then obviously it is divergent. It is divergent in nature. That means it goes to some infinite, even though I am moving my n tends to infinity. This is not going or tending to some specific point, rather it goes to infinity. Okay, so if I try to find out the limit n tends to infinity, so what I will do that I will take n common here. So it will be n square I plus 2 by n square 2 by n, if I take n common outside, divided by I n square can be cancelled out, and now we are in a position to put, so limit n tends to infinity I plus 2 n square divided by I is nothing but I. So that means this sequence, if you try to put 1, 2, 3 or the value of n, you will find that in the previous case whatever the function is, whatever the sequence is given, it was going to the value 0. Here we find it is going to the value I. So that means if this is my point, so I is here, so the point will gradually go to this point I. So that means it is converging to that particular point, which we call the converging point here. In this case here it is I. You can also verify, by the way, you can also verify that this quantities, real and imaginary part at n tends to infinity goes to, okay, let me, so I need to find out this limit, right. So I can separate it out to real and imaginary part. So if I do that, then it will be, if I make the square, so it will be minus of n square plus 2 I n plus 4 divided by I of n square. So limit n tends to infinity, if I multiply with I, then it will be minus of I multiply minus I, so that the minus I into minus of n square plus 2 I n plus 4 divided by n square. So real and imaginary part I can separate out. So one limit n tends to infinity, one, the real part is how much? The real part is, when I multiply, it will be 2 n divided by n square. This is the real part that I should have. This is the real part that I should have. What will be the imaginary part here? The imaginary part, if I put the n tends to infinity, what value I will get? 0. What will be the imaginary part of this quantity? Imaginary part is this one. So it will be n square minus 4 with I divided by n square. Now if I take n square common and if put n tends to infinity, then this term will not be there, only I will remain. So this value will be I. So as I mentioned that when limit n tends to infinity, Zn goes to L, which is A plus IB, then the real part of Zn with the limit n tends to infinity should be A, and limit n tends to infinity imaginary part of Zn should goes to B. In this case you can find that the real part of goes to 0 and imaginary part goes to I. That means my L is equal to 0 plus I. By the way, here the imaginary part I am talking about, not the imaginary part, I am taking also I here. So in principle, when I am talking about imaginary of these things, this I shouldn't be there. So then the limit should be 0 and 1, and then the value will be something like this. My A is 0 and B is 1 in that sense. So there is a slight I should say it is a mistake, because when I am taking the imaginary part of z, I should take only the imaginary part without taking I. So, that is why this is will be the case, and I will get 1 here. Okay. So, I believe you understand how these things are working. So, let me go to another example. My next example is something like n plus I to the power n divided by root over of n, and I need to find out whether this is converging to some point or not. So, again I need to do the same procedure. Limit n tends to infinity, quantity is n plus I to the power n divided by root over of n. So, limit n tends to infinity, I can separate out into two part, n plus I to the power n root over of n, which is n tends to infinity root over of n plus I to the power n by root over of n. So, when n tends to infinity, this quantity can go to 0, but this quantity is infinity. So, the value is infinity, that means this sequence is diverging, this diverges, this sequence is diverges. Okay. Next, another example. And it gives me something like this: 3 plus ni divided by n plus 2 ni. 3 plus ni, n plus 2 ni. So, now I need to find out whether this sequence is converging or not. If it is converging, then again we need to find out these things. So, it will be 3 plus ni divided by n 1 plus 2i, right. So, when n tends to infinity, so my first target will to remove this n, to make it 1 by n and remove this n. So, if I do that, then if I divide these things, so it will readily be, if I take n common out of there, so it will be 3 divided by n plus I divided by 1 plus 2i, this. Now, n tends to infinity I can put, because this quantity will going to vanish. So, by result here, after putting the limit, is something like 1 divided by 1 plus 2i. Again I need to put this as a plus iv form, so that I can find what is the value where it is converging, what is the exact value. So, I should multiply with the complex conjugate here. I will multiply a plus 1 plus 2i. So, 1 minus 2i I will multiply. So, I will have here 1 plus 2i, 1 minus 2i, and these things is how much? I 1 minus 2i divided by a plus b into a minus b, a square minus b square, here minus b square means 4, minus 4. So, it will be just 5, 1 plus 4 5, a plus b into a minus b, a square minus b square. So, I is there, so minus will be plus. So, 1 plus 4, it will be 5. So, then the limit is something like, if I multiply I, then it should be 2 1 into 2 2 plus I by 5. So, it is just 1 by 5 2 plus I. This is the point where this sequence will going to converge. That is the point 1 by 5 2 plus I, where the sequence is going to converge. Okay, after having a lot about this, so now I believe whatever the sequence is given to you, you can readily understand whether this is a converging or not. It is not a very big deal to find out whether it is a converging or not. You just put the limit n tends to infinity, and when you put n tends to infinity, then you will find that this quantity, which is the nth term of this under the condition n tends to infinity, you will find that if this is going to a specific value or specific point, here in this case this point is 2 by 5 plus 2 by 5 plus 1 by I 1 by. So, 2 by 5 is somewhere here and 1 by this is somewhere here. So, some point here it is converging, this is converging somewhere here in this point. So, I mean it depends on how this sequence is given, and every time the procedure is same, and you will find a specific point. If it is converging, you will find a specific point where it is converging. After having that, so today I would like to introduce another thing before completing the class. It is called series. Sequence we learn, now we need to learn series. So, series is something where I have say this quantity Zn, some quantity I am going to add, say first one is Z1, second one is Z2, third one is Z3 and Zn and so on. And it is basically the, we called it as partial sum, and then if I put the partial sequence of the partial sum, then I will have this. So, what is the sequence of the partial sum? So, this is the sequence of the partial sum. So, what is the meaning of partial sum? Say S1 is Z1, S2 is Z1 plus Z2, S3 is Z1 plus Z2 plus Z3 and so on. So, that means when I put this entire thing, I am basically putting Sn. Sn is nothing but Z1 plus Z2 plus this quantity. So, it is the series is, it is called the partial sum because I have one quantity, then I have two quantity which is sum over this, then I have three quantity, then I have n quantity, and this all quantity I defined by S1, S2, S3, Sn, and this I put here. So, this is the partial sum, this is some sort of sequence I have. So, every time I am adding, I am getting the new terms. So, when I put the Snth term, then it is basically gives me the series of all quantities. Again, if it is, if this entire sum limit n tends to infinity Zn nth term of this quantity, if it goes to some value say Zl, then we can say that this sum is convergent. That means I have different kind of terms in my hand which we am going to adding, and then try to find out the nth term whatever I am going to add. If n tends to infinity, it is some finite value, it goes to some finite value. So, I am adding the term, but this goes to some finite value, then we call this is convergence. So, today we do not have much time to discuss it more. So, in the next class we will start here, I will conclude the class here. in the next class we will start from this point and try to find out how the series will going to evolve and how to find out the convergence of series and all these things. So, with this note, let me conclude the class here. So, see you in the next class where we will going to study more in detail what is the meaning of series and all these things. So, see you in the next class and thanks for your attention.